The 2021 Wisconsin Science Festival. Hybrid, hands-on, and virtual. Events throughout Wisconsin for all ages. Discover the wonders of science and the power of knowledge with a focus on fungi with scientists, live Q&A sessions, science experiments, and more. Plus, PBS Wisconsin Education launches 2 new interactive labs in the Meet the Lab collection. Full schedule at wisconsinsciencefest.org. Curiosity unleashed.
Hello, fellow scientists. I'd like to welcome you to the Wisconsin Science Festival online field trip, the Physics Experience. Thank you for joining us today. My name is Ashley from the Wisconsin Science Festival team, and we're here with our special guest, Mike Randall, for this field trip experience. So, how can you participate today? Well, you'll notice that your picture and audio are muted. But if you have any questions you'd like to ask, you can use the Q&A feature and the chat. As soon as you have a question, go ahead and type that in right away, and I'll ask the question for you out loud during the field trip. This field trip will be recorded, and as always, we ask that you do this and all activities at the Wisconsin Science Festival with a responsible adult. We'd also like to thank all our sponsors and partners that make the Wisconsin Science Festival possible. You can find out more activities and events during the Wisconsin Science Festival at wisconsinsciencefest.org. With that, we're excited to get started. Take it away, Mike.
There we go. Hi, everyone. My name's Mike Randall. I'll be your presenter for the Physics Experience. And hang on just a second. Does everything look yellow to you?
Just a little yellow, yeah.
Let's try it again. Hang on. Every once in a while that happens. Oh no. Okay, well, while I'm fiddling around with this, I'm going to talk to you about who I am and what we're doing here. So I'm going to turn my camera off for just a second. I know how to fix this. There we go. So sorry for the technical difficulties, but again, my name's Mike Randall. I'll be your presenter for the Physics Experience today. Today we're going to be talking about physics. We're going to talk about what physics is, what it has to do with all of you. Mostly we're here to have fun today. And I also want to tell you a little bit about myself. I actually am a physicist. I went to college and I learned physics, and that's better. I'm also a former rocket scientist. I'll talk more about that later on in the show. But how I got started in physics was my dad. I was lucky. My dad was a scientist too, and he had me doing science experiments from the time I was 3, okay? And so I was lucky. I was doing all this really cool stuff, but I know that not everybody has a scientist for a parent. So I get to now share what my experiences are with science with you, and maybe have you look at the world a little bit differently, and maybe you'll get excited about science too, like I did. So we can't talk about physics unless we know what physics is. So let's start off with, there's a lot of different ways you can define physics. Here's my definition. Physics is the study of stuff. This room is made out of stuff. This ball's made out of stuff. You're made out of stuff. I'm made out of stuff. But scientists have a different word for everything. Scientists don't call stuff stuff. Scientists call stuff matter. Matter. Okay, so physics is a study of matter, like this ball. But there's more. Physics is also the study of how you move stuff around. What gives you the ability to move stuff around? It's a one-word answer, starts with the letter E. Energy. Energy. Energy is the ability to do work. Energy is the ability to do anything. So physics is a study of matter and energy and how those two things play with each other, how they interact. Now this covers a lot of things. It covers movement, like throwing a ball. It also covers sound you could hear, light you can see, heat you can feel, electricity, magnetism, and then a whole bunch of other stuff lumped together in a category called modern physics. I'm going to give you a really cool demonstration of that later on in the show using lasers. But we can't talk about physics without talking about one of my favorite dead guys. This would be Sir Isaac Newton. Sir Isaac Newton was widely regarded as the father of physics. He's a very smart guy, figured a lot of cool stuff about how the world works. He lived about 300 years ago, which explains why he's dead. Anyway, one of the most famous things he figured out was he had a lot of ideas about movement. Maybe you've heard of Newton's 3 laws of motion. So I'm going to give you my version of those right now. So for Newton's first law in my version of it says stuff wants to keep doing what it's already doing. Stuff, like the stuff in this basketball, wants to keep doing what it's already doing. If something's sitting still, it wants to keep sitting still. If something's moving, it wants to move in a perfectly straight line at exactly the same speed forever, or until something outside of it pushes or pulls on it. That's it. Newton's first law, that was pretty easy. Now for Newton's second law says that force, mass, and acceleration all go together. Force, mass, and acceleration go together. What's that? Well, force is easy. It's that push or pull I was just talking about. So force is just a push or pull. Mass, okay, we know this ball is made out of stuff, which scientists call matter. The measure of how much stuff is here, how much matter, that measure would be called its mass. So mass is just how much stuff is there in something. And acceleration is easy too. Acceleration is simply a change in speed or direction. Okay? So those three things go together. How hard you push or pull, how much stuff there is in something, and how it accelerates or changes directions, how it speeds up or changes directions. So, for example, if you were in this room and I handed you this basketball, I said, throw the ball to me, what would you do? Well, chances are you would push on it, right? That's a force. Now, how hard you pushed, you would already figure that out. So this is something I didn't mention earlier. You are all physicists. Yeah, you are all physicists. And this is just one of several demonstrations of that I'm going to give you today. You're really good at this stuff because you knew, if I handed you a ball, you would not only know to push it to get it to me, but you would know how hard to push it. Because you could say, okay, I can get an idea of how much stuff there's in this ball. I know how hard to push it to get it to accelerate fast enough to make it over to him. Okay? Now, but what if I wasn't throwing this ball? What if I handed you this ball? This is called a medicine ball. You can see that it has a lot more mass. It's quite heavy. Would you push this ball the same as before? I've done this demonstration hundreds of times where I would hand the ball to people and I wouldn't give them any coaching up front. And I'd say, just throw that ball to me. And they always threw it to me. It never dropped on the floor. They never overshot. Everyone knew how to throw this ball to me. Because they knew, just like you know, that with more mass, you have to apply a bigger force to get the ball accelerating fast enough to make it over to me. That's proof that you are a physicist. Because you all know how to apply Newton's second law. Wow, you didn't even know that. You're physicists. Okay, for Newton's third law, I mentioned earlier that I was a rocket scientist, for real. I used to work on the space shuttle main engines and other rocket engines. So I happen to know that Newton's third law is often referred to as the law of rockets, and here's why. Yeah, I know this isn't a rocket, it's a leaf blower, but the idea is still the same. So in a leaf blower, a lot of gas goes this way. Sir Isaac Newton would have called that the action. And the rocket goes this way. That's called the reaction. So So that's Newton's third law, by the way. For every action, there is an equal and opposite reaction. Or as I like to say it, if you push against something, it pushes back. Okay, what does that look like in reality? Well, let's find out. I get to be my own camera person. So I have a turntable here on the floor. I know you can't see it, but it lets me kind of spin around. Oops, if I'm careful. There we go. So what do you think will happen if I turn this leaf blower on? Ah. Just kidding. I love my job. But you saw that. The gases went that way, and I went the other direction. Newton's third law. So now you know all three of Newton's laws. So let's talk about energy. It's another very important thing. Energy, by the way, there's many different forms of energy. We've already talked about some kinds of energy already, but there's many different forms of energy, but they all have two weird things in common. Weird fact number one, you can't make energy. Well, don't feel bad. I can't do it either. Nobody can. Weird fact number two, you also can't get rid of energy. What? You can't make energy, you can't get rid of it. You can only turn it from one form to another, and you are all experts at this, and I'm going to prove that to you right now too. Physicists, put your hands up in front of you like this, put your hands together like this, and start rubbing your hands together. Keep rubbing those hands together. And stop. What did you just notice? Well, you probably noticed that your hands started getting warm, right? Heat is a form of energy. We're going to talk more about that later. Heat is a form of energy, but you didn't make heat energy. You had to turn some other kind of energy into heat energy. What are my hands doing? They're moving, right? Movement is another form of energy. Scientists even have a word for that. They call it kinetic energy. Kinetic energy, energy of movement. So that somehow that kinetic energy got turned into heat energy. How'd that happen? Well, there's this force. Force is not energy. Don't confuse them. But there's this force called friction. That when things are touching, it kind of makes things stick together. And when things are touching and moving, friction is the force that turns that movement energy into heat energy. Okay? So now we know how it happened. But wait, there's more. Where did the movement energy come from? Have you had anything to eat today? There's a reason we eat food. There's energy stored in the food. Stored energy is something that scientists call potential energy. Specifically for food, they'd call it chemical potential energy, but it's stored energy. So you eat food, and energy is stored in your body until you need it to move. Your body sends that energy to your muscles. Your muscles turn that into movement energy. Friction in your skin turns that to heat energy just that quick. You go from one kind of energy to another to another. This happens all the time. You do this all the time. You are such experts at this, you don't even notice you're doing it. You are such experts, you don't even notice you're doing it. Experts, like you ever watch an expert basketball player running down the court to do a slam dunk? They never do this. Left foot, right foot, bounce, left foot, right foot, dunk. They don't do that. They don't have to think about it. They're experts. They just run down the court, slam dunk the ball. It looks great, right? You are experts in exactly the same way when it comes to turning energy from one form into another. You do it all the time. You're doing it right now. And you're such great physicists, you don't even have to think about it. Isn't that cool? Now, next thing we're going to talk about is something called states of matter. So we've talked about energy. Now we're going to talk about stuff a little bit more specifically. States of matter. I'm going to stand back here. Okay. All the ordinary stuff around us is made of little teeny tiny things that sound like a boy's name. Starts with the letter A. Do you know what I'm talking about? Atoms, right? Atoms. Okay, so atoms are super, super, super tiny. We can't see them with our eyes. But I'm going to represent atoms with these glass marbles. So I've got this bottle's full of glass marbles. So it's packed pretty tightly. So you can hear these atoms are kind of jiggling around, but they're not trading places. This state of matter would be called a solid, like the walls in this room or my head. Here's another state of matter. In this state of matter, the atoms can move past one another. If you put them in a container, they'll take on the shape of the container. They won't necessarily fill up the container, though. They've got a little bit more movement going on to them. This state of matter would be called a liquid, like the water you drink. Another state of matter. This state of matter, the atoms are moving around really fast. If you put them in a container, they will fill up the entire container. They're zipping around. This state of matter is called a gas, like the air you breathe. Solids, liquids, and gases. Have I missed anything? Yep, I missed a real important one. The one that you saw at the beginning of the show. This is called a plasma. If you take any ordinary matter and you dump a lot of energy in it, it could be heat energy, it could be light energy like from a laser, it could be high voltage electricity. You will take that matter and you will break the atoms. Yeah, atoms are made of even smaller things. So if you dump a lot of energy into an atom, you could break loose these little teeny tiny things called electrons. So what a plasma is a mixture of these free-floating electrons and atoms that are missing electrons. Those are called ions. We're going to talk more about those later on. So this is a plasma we're making with high voltage electricity. Plasma is really important stuff. If you look up in the night sky, 99% of what you see will be plasma. Our own sun, by the way, is a giant ball of plasma. So if it wasn't for plasma, we wouldn't be here having this conversation because the sun's providing all the energy for, pretty much all the life on Earth. So very important stuff. So solids, liquids, gases, and plasmas. One thing that's important to notice, I mentioned these little atoms can move around. We're going to kind of go back to something called heat energy. Remember I mentioned heat energy? A lot of people have heard of that. They don't know what it is, and it's really simple. Heat energy is just how fast or how slow are the atoms in something jiggling around. That's it. So if the atoms are moving very slowly, that means that it's cold. We would call it cold. It doesn't have a lot of heat energy in it. If the atoms are moving around really fast, we would say that's hot, or it has a lot of heat energy in it. Okay. Now that we know that, we can now play with some of my favorite stuff. This is called liquid nitrogen. This is crazy, crazy cold. What this is if you take the air, like in this room, and you take a lot of the heat energy away from the air in this room, it turns into this. So liquid nitrogen. This stuff is 321 degrees below 0 Fahrenheit. Minus 321 Fahrenheit, minus 196 Celsius, 77 on the Kelvin scale. And I'm actually going to zoom in a little bit because I'm going to show you something really, really fun. Oops. Let's zoom in a little bit more. Now, two things. Number one, liquid nitrogen is seriously, seriously dangerous. If I don't handle this right, I could hurt myself and go to the hospital with something that hurts really bad called frostbite. Okay? But I went to college, so I learned how to handle this correctly and safely, so I've never been hurt by it. And the really cool thing is that if you've gone to college and you know how to handle this stuff correctly and safely, it's a lot of fun. See my finger? Don't ever try this until you go to college. I'm going to stick my finger in the liquid nitrogen. What do you think is going to happen? Boop. Nothing. Wait a minute. Like I said, I'm not going to tell you how I did that, but when I went to college, I learned some really interesting stuff about how liquid nitrogen works, and it allowed me to do that without harming myself. Don't try that until you go to college. Now, let's do that experiment, shall we? I'm going to stick this balloon in the liquid nitrogen, and I'm going to leave it in there. What do you think is going to happen? Whoa, time out. This is a trick question. This is more proof that not only are you physicists, you're also scientists. So you ask a scientist a question like that, and a thought immediately pops in their head. It's a guess. It's a guess as to what's going to happen next. Scientists even have a word for that. They call it a hypothesis. They call it a hypothesis. They call it a hypothesis. Yeah, there we go. It's easier to say it's a guess. It's a guess. So I bet you, when I asked you that question, you all had guesses pop into your heads. But scientists don't stop with the guesses. They set up an experiment and then they observe that experiment to see if their guess is correct. That's your job, scientists. Keep your eyes on this balloon. The balloon is in the liquid nitrogen. You notice anything happening? Well, it didn't pop. Wait a minute, look up here. It's starting to shrink. So it's sprung a leak, right? No, we are taking heat energy away from the little air atoms inside this balloon. Those air atoms are now moving very slowly, which means they're not running into the insides of the balloon as hard. That means the pressure inside the balloon is dropping until it collapses down into this sad looking thing. But all the air is still in there, and there's plenty of heat energy out here in the air in the room. So as the heat energy from the room goes back into the balloon, the little air atoms inside the balloon start moving faster and faster. They start running into the walls of the balloon harder and harder. The pressure's going right back up. Pretty soon the balloon is right back to normal, like nothing ever happened. Whoa. I'll get that later. Now, I mentioned liquid nitrogen was dangerous, but it's dangerous for a couple reasons at least. Here's an interesting fact. If I had this one container full of liquid nitrogen and I warmed it all up to room temperature, this one container of liquid nitrogen would make almost 700 containers of gas. Seriously, seriously, you never put liquid nitrogen or dry ice, either one, into sealed containers. It's a really bad idea. Why is it a bad idea? Well, who said that? Well, it's a good question. I've gone to college. I know how to do this correctly, safely, so I'm going to do it. Don't you try it, though. So I have some, that little ladle there. It's got some liquid nitrogen in it. I have a cork, and I got a hammer. This is a really bad idea. Ooh, I'll get that cork later. But what happened? That liquid started boiling. It turned from a liquid into a gas. The gas took up a lot more room, 700 times more room. But it was in a sealed container. So the pressure went up until, boom, it shot that cork out. Made this into a cannon. Or if you really sealed it up good, it could be called a bomb. Bottom line, very dangerous. Don't try that until you've gone to college and learn how to do it right. Now, some of you may have noticed that there seems to be a lot of smoke around this thing. This is so cold, it's actually making a cloud. Isn't that amazing? See, there's water all around us in the air. We can't see it. It's an invisible gas called water vapor. But if you take enough heat energy away from that gas, it turns into tiny little droplets of liquid water, which we can see. That's what a cloud is. Little tiny droplets of liquid water. Now, as amazing as that is, what I want you to pay attention to right now is, what does the liquid nitrogen look like? Might be a little hard to see from here, but can you see that? It looks just like water. Seriously, don't drink it. You now know enough about liquid nitrogen to know why that's a really bad idea. You also know it's a really bad idea to put liquid nitrogen into a sealed container. No. This is no ordinary container. This is called a dewar. It is designed to carry liquid nitrogen. So any of the gas inside of here that turns back into, or any of the liquid that turns to gas, the gas can leak out harmlessly. This does not turn into a bomb. It does help keep me from spilling it between shows, though. So now I can set that aside. All right. Now let's talk about, I just mentioned, I used a word called pressure a little bit ago. Specifically, let's talk about air pressure. Interesting fact, right now we are sitting at the bottom of an ocean. Yes, you too. You're sitting at the bottom of an ocean. And it's probably an ocean of air, unless you're sitting at the bottom of your swimming pool right now watching this. I don't know. But we're sitting at the bottom of an ocean of air, and that air is heavy. See the end of my thumb here? It's about an inch wide and an inch high. Any place I could cover up with the end of my thumb, the air's pushing down with the weight of a bowling ball. So right now I got lots of bowling balls worth of air pressure on my head. You do too, by the way. So why don't we notice it? Because they balance out. So if the ones on this side are balanced by the ones on this side, I don't really notice it. But what if I create an imbalance of air? So I've got these things here. People know these, might call these suction cups. Nature does not suck, it pushes. And no, they're not magnets either. They're not sticking together until if I push them together a little bit and then I squeeze these handles. Now if I try and pull them apart, I'm genuinely pulling as hard as I can. I can't get them apart. How can that be? Well, remember all those bowling balls with the air? They're all pushing on the outside, pushing them together, but I squeezed most of the air out from between these. So there's really no bowling balls on the inside pushing back out. I created an imbalance of forces. I would have to pull with about 200 pounds of force to pull these apart. Or, because I know the physics of it, I can just unclick the handles and let the air back in and they come right apart. Just like that. Now there's another guy who did one of my favorite dead guys who did some really cool stuff with air pressure. His name was Bernoulli. I just like saying his name, Bernoulli. He figured out that when air is moving faster over something, like this guy here, when air is moving faster over something, the air pressure it's not pushing down as hard. So this thing right now has got bowling balls worth of air pushing on all sides. All the forces are in balance. But if I blew air over the top, there wouldn't be as many pushing down. So let's see what happens if I blow air over the top. So I get my trusty leaf blower out here again. I'm going to go to a little bit wider view. Excuse me just a second. Let's do this. I get to be my own camera person. There we go. What will happen if I blow over the air over the top of this ball? No strings. Whew. Why did it do that? Well, if I let go of this ball right now when there's no air blown over the top, what do you think is going to happen? It fell to the ground. That's because there was some other force we weren't talking about. It's the force of gravity. So gravity, we all know about gravity. It's what pulls everything to the ground. When I blew air over the top of the ball, though, now there's not as much air pressure pushing down, but there's the same amount pushing up. If I aimed it just right, the air pushing up exactly balanced the force of gravity pulling down. We created a new equilibrium, an equilibrium that allowed this ball to hover in midair. Now, a lot of you may already be experienced with this and not even realize it. Have you ever flown on an airplane? Notice the wings? The wings have a special shape. They're curved on the top, but they're flat on the bottom. When that wing slices through the air going over the top of the wing has to travel further than the air going underneath. If it has to travel further, it means it has to go faster. Faster moving air means less bowling balls with the air pushing down. It's the air pressure under the wing that then lifts the wing and the airplane up. See, physics is everywhere in your lives. Isn't that fun? All right. Now, I promised you a demonstration of modern physics. How are we doing for time? Yeah, we're doing pretty good. Modern physics is where Sir Isaac Newton got it wrong. Wrong. Okay, now he was a really smart guy. And he came up with a lot of ideas about how the world works, including a lot of ideas about how light works. And for 200 years, scientists thought his ideas were it. But about 100 years ago, scientists were experimenting with light, and they were getting results totally different than what Newton predicted, and it freaked them out. Now, to show you why they were so freaked out, I'm going to do a couple things. I'm going to use a different camera here, one's a little better with light. I'm also going to use some lasers here, okay? So let me set up my camera first. Hopefully I can do this quickly. Da-da-da. I like my automatic camera, but the one thing it does not do well is it doesn't handle light, low light levels very well. So let me switch over to my other camera. There we go. So I also need to talk about lasers. I got some laser pointers here. Let me turn the room lights off. There we go. So I've got some lasers here. I have a red laser, I have a super bright green laser, and I have kind of a wimpy purple laser. Now, lasers like these are very dangerous, and I'll bet you know why. These are so intensely bright, if that shines in your eyes, it could permanently blind you, okay? Even these little laser pointers, which I'm sure many of you have around the house, you might play with your cats with them. Be super careful with these. In fact, really don't play with lasers of any kind until you go to college and take laser safety training classes, okay? Just trust me on that. Now, I've taken those classes so I can play with these all I want. Now, you might have noticed I was aimed at a screen earlier. That's no ordinary screen. It's a glow-in-the-dark screen. Now, you guys all know about glow-in-the-dark stuff. Before it will glow, you got to shine some light on it to make it glow. That makes sense. Now, if Sir Isaac Newton were here, he'd say, hey, that super bright red laser thing of yours, that is so intensely bright, that laser will immediately make that screen glow. That makes perfect sense. Except it doesn't work. You don't see any glowing. I don't see any glowing. Huh. Well, maybe it wasn't bright enough. Let's try my super bright green laser. This is so intensely bright. Well, it doesn't make it glow either. Hey, if Sir Isaac Newton were here, he'd be freaked out right now. Well, the only one I got left is this wimpy purple laser. So we try that. Self-portrait, glasses, beard, eyebrows, nose hair. Yeah, I'm not a very good artist. That's why I became a physicist. But why? Why will this wimpy purple laser leave this beautiful green glowing line? And my green and my red, where'd my button go? My red lasers do nothing. You know what? It took another one of my favorite dead guys to figure this out. And you've all heard of his name. You ever heard of Albert Einstein? Albert figured it out. He said it's not about how bright the light is, it's about how much energy there is in the light. I'm going to switch back to my other camera. There we go. Oops. Let me turn that off and turn my rainbow on. You've all seen rainbows before, right? So Albert Einstein said, what we see as different colors is really different amounts of energy in the light. So, blue light, which is on top, has more energy than green light. Green light has more energy than red. What we see as different colors is really different amounts of energy in the light. And because they figured that out reasonably recently, that's why they call that an example of modern physics. All right. All right, let's talk about electricity. Yeah, we're still doing really good on time here. So electricity or electrical energy is another form of energy, right? It's another way to get things done. But again, a lot of people don't know what electricity is. It's very simple. Remember those little electrons I talked about earlier? Electricity is the movement energy of those little electrons or other charged particles, but it's usually electrons. Charged particles, what does that mean? Well, we'll talk about that in a second. So there's different ways to get electricity moving around. Here's one. My flashlight's got a little crank on the side of it. This is called a generator. What actually is going on inside of this is there's a little magnet inside that is spinning near a coil of wire. The magnetic field pushes on the little electrons in that wire, gets them moving, gives them a burst of that kinetic energy we talked about earlier. Enough energy to do something useful, like lighting up a light. Most of our electricity comes from gigantic versions of these. Here's another one. This is called a Tesla coil. It's named after the famous inventor Nikola Tesla. This does something very special. It takes those little electrons and it shakes it back and forth really hard and really fast. Let me see if we can zoom in on this a little bit. And it looks like this. You see that spark there on the end of the tube? Anybody think that spark is hot? Oh yeah. It's really easy to turn electrical energy into heat energy. So let's see what that looks like. So I have a thing here. I've got a bottle here that's got car fuel in it. It's got a little bit of alcohol in it. But this doesn't do anything unless you light it on fire. So in your car engine is also a little thing called a spark plug. That electrical energy from that spark can easily be turned into heat energy, enough heat energy to light this on fire. Want to see what it looks like? Okay, there's a cork on top. Let's see if we can watch where this goes. Okay, 5, 4, 3, 2, 1. Whoop. Boom. I'll find the cork later. All right. There we go. Last but not least, I got this thing here. This is called a Graaff Generator. You guys in the wintertime ever notice that when you rub your feet on the carpet and then go reach to something metal like a doorknob, zap, you'll see a spark jump across? There's a name for that kind of electricity. It's called static electricity. You've heard of this. What you may not realize is that when you're scuffing your feet on the carpet, you're actually scraping electrons off the carpet and storing them on your body. Electrons hate that because electrons have something called an electrical charge, a negative electric charge to be specific. And think of it like a little force field. So if you put two electrons together, they want to push apart from each other. Just like if you put two north poles on a magnet together, how they'll push apart. Electrons are the same way. So as soon as you give these crammed together electrons a way to escape, like jumping off your finger onto the doorknob, zap, they jump off and make that spark you see. Now this machine does this for me. We'll zoom in and out a little bit here. There we go. This is what it looks like. Oops, well, I guess all my lights aren't going to come off. Can you see those sparks there? Looks like little baby versions of lightning. And if you could hear the sound, it sounds like a baby version of thunder. By the way, this is harmless. Ow, ow, ow. It doesn't feel very good, but it's not going to send me to the hospital. If you see real lightning or hear real thunder, you get indoors quick, okay? Real lightning, although it's made in a similar way, it's much more powerful, it's much more dangerous. This is quite harmless. Now, I mentioned I was a rocket scientist, right? The space shuttle main engines that I worked on, pound for pound, are the most powerful machines ever built by man. 500,000 pounds of thrust. Only problem is they go through all their fuel in about 8 minutes. And after that, they're dead weight. But NASA's already been using a new kind of rocket called ion propulsion. I actually have an ion rocket right here. Let's turn it on. Ah, there it goes. That high voltage electricity is going out to little points on the back end of each rocket. And just like the electrons jumping off your finger, the electrons are jumping off that pointed part. They go that way by Newton's third law. They go that way, the rocket goes the other way, right? Ion propulsion. So I know 500,000 pounds of thrust versus not very exciting. But there's a mission that NASA's already flown called the Dawn Space Mission. I encourage you to look it up, DAWN. The Dawn Space Mission, their thrusters, would take their vehicle from 0 to 60 in 3 days, like really slow acceleration. But they could be run, those engines could be run at full thrust for up to 5 years before they ran out of fuel. So it added up. They go faster and faster, just like these rockets are going faster and faster. You notice that? Why is that a big deal? Some of you may be going to Mars someday, for real. You might be exploring Mars. If we use regular rockets to get there, the trip would take at least 300 days. That's almost a year. But if we can get this kind of technology perfected, you could make the same trip in maybe 40 days. Almost a year versus 40 days. I vote for the 40 days, okay? I'm sure you would too. So that could open up a whole new way of exploring our own solar system. Now, one thing I briefly mentioned before, electrons are super powerful for their size. They really push apart very strongly. But they're so super tiny. But so some of you may not really think, well, that's no big deal. Check this out. So these are a bunch of metal pie pans. When I turn this on, these are made out of metal, so electrons travel easily through metals. It's called, they're good electrical conductors. So this metal ball will be covered in electrons, this will be covered in electrons, electrons next to electrons. What do you think is going to happen? Flying saucers! Ha ha ha! And a big mess that I get to clean up. Okay. So, as always, I've got way more toys than time, but I want to leave enough time to get some Q&A in. But here's what I want to leave you with, if nothing else today. I hope you had fun. Learn how your world works. That's what physics is. It's another definition of physics. Physics is the science of how your world works, how everything works. Learn how your world works. Look, you may not all go on to become rocket scientists, although I wouldn't have a problem with that. But what do you like to do? Do you like music? I've done whole shows on the physics of music. Do you like cooking? I've done whole shows on the physics of cooking. Do you like dancing? I've done whole shows on the physics of breakdancing, okay? Look, physics is everywhere in everything you like to do, and you're already physicists. But the more you learn about physics and apply that knowledge to whatever it is you like to do, it's going to make you a little better at it. Like the people in the Olympics. I will tell you, the people who won medals in the Olympics did their physics homework, because understanding how the world works and applying that knowledge made them a little better at something they were already pretty good at. But sometimes that can make the difference between getting a medal or not. But even if you're not competing, if you're just doing something for fun, if you're doing better at something that you already like to do, doesn't that mean you're having more fun with your life? I believe that's true. I've had a ton of fun doing these shows. I'm so happy that Wisconsin Science Festival invited me to do this show for you. Thank you very much for having me. And now we've got some time for some Q&A. So what do we got?
That was amazing, Mike. Thank you so much for that. So I have a question. So I think that was some great advice, and I'm wondering, like, what was the first thing you think that you could remember really got you into physics?
This may not be exactly physics, but I got to tell you, I was always curious because my dad always encouraged me to explore. Well, my dad left his camera sitting out once. So this is back when we had film cameras. I knew nothing about a camera, but I started playing with it, the buttons and the knobs and stuff. And there's this knob that advances the film. It only goes one way. And I started freaking out. I wanted to I didn't want him to know I was playing with the camera because I'd been forbidden to do that. So I was going to turn it one way and then put it back so he wouldn't notice. But it wouldn't go back. And I kept trying to make it go back and go back. And it's like I started really freaking out and crying. And my dad came in. And rather than getting angry with me, he sat me down and he opened up the camera and he showed me how it worked. And it's like it showed me, like, I don't have to be afraid about it. exploring things and learning how my world works. Like he gave me the space to do that. It's another thing I want you to take away from it. It's okay to make mistakes. It's okay to give the wrong answers, as long as you then learn from that. Okay. So really, I've made many mistakes in my life, but I've learned from them. And the more you learn, then you can start relaxing. You can have more fun. You can be goofy and silly like I am, and not worry about making mistakes. And that stuff comes from. If you're afraid of making mistakes, you're never going to go out and change the world.
Amazing.
All right.
Okay, so we have time for one more question. So, what are some easy physics activities for elementary students to do at home?
I don't have it set up here, but one of my very favorites is very easy to do. Let me grab something off camera here. This is kind of a giant size version, but get some empty soda cans, not these giant ones, but just a regular soda can, wash it out. And you know, they have kind of a double rim on the bottom. You can see it easier on this big can. There's a rim here, there's a rim here. So if you lean it over, both rims could touch a tabletop at the same time. But of course, if you let go of that, it's just going to fall over, right? But with your regular soda cans, try that, and then get a measuring cup that measures, preferably one that measures in metric. Put 100 milliliters of water, measure out 100 milliliters of water, pour it inside, and try that same thing again and see what happens. It's something to do with something called the center of gravity. And I'll just leave it at that. There's websites that'll explain that too, but it's just like, I encourage you to try that. It doesn't cost anything to try, and the results will astound you. And it looks like magic, but it's really basic physics.
That sounds super cool. And remember, if you want to try this experiment, write out what you think will happen before you actually do the experiment, and that'll be your hypothesis. So thank you everyone for joining us at the Wisconsin Science Festival field trip, the physics experience. Thank you, Mike, so much for this super amazing show. A recording of this field trip may be available, and we will follow up with teachers about that. Remember that the Wisconsin Science Festival continues with events hosted from organizations across the state that you can participate in. Just check out wisconsinsciencefest.org for more fun science, and we'll see you there. Thank you all so much. Thank you, Mike.
Bye-bye.